Engineering 2. Woo. Can you guys hear me? Okay. Let's start with sharing my screen and let's do a quick review of what we did last time. It's right here. So again, bigger, and then we'll start with the position. All right. So what about yay? Let me get some light. Come on, computer. There we go. A little light here. So the quality is slightly better. Okay, so you guys recall last time I told you guys that we are bounded by rule number 1, which is the envelope principle. Or we call it rule number 1, or sometimes they call it the envelope principle. So out of the box, your part it is bounded by a minimum and a maximum boundary, right? The LMC and the MMC. I can graph and I could get this part within the envelope. And if I were to have my part when it's small, it can fit in there and it has a bunch of wiggle room to move, a bunch of wiggle to have form variation. But as I move away from, if I got all the way to MMC, and I want to assume that this is MMC, the biggest I can get, say MMC is actually like this, right? MMC. My envelope is MMC. So if I were to put my form, I were to put my part within the envelope cannot have any form anymore. However, as I move away from MMC, there is some form variation. I also told you guys that if I were to have a feature, a run feature, but now I were to apply a straightness on a feature size, then I automatically override rule number 1. So rule number 1 now it says, you know what, I'm going to open the envelope and I'm going to allow you to have a little bit of variation. Okay, just a little more. So open the envelope. Okay, and that envelope is going to allow you to have a variation in terms of geometry imperfection. Okay, so that means if my part gets to be crooked, my part will have this variation to play with, right? Actually, let's make it here because it doesn't see. Let's say something like this, right? So now because I made it open the envelope, I have some form variation. And in my case, if you guys remember, what I'm controlling is the right median line for the straightness, and my part gets to live within the cylinder polygon, which is the cylinder specified on the feature control frame. Okay, I told you guys that we can assume this in terms of the worst case condition as the worst case condition. For a pin is the biggest it can get plus the quickest it can get. So let's say biggest I can get plus the quickest I can get. Let's say that I'm making this pin as the worst case, something like that, right? And it is the biggest I can get, and also the quickest I can get. Let's say that this boundary is called the virtual condition. Okay, I can also grab my hole, and I can do the same concept, right? So let's say that I got in a hole that it was big, right? It was small, and then I even made it even smaller than it was before, right? Because I remember once I have a hole and I have any imperfection, the hole actually will act smaller than what it actually is. Okay. So the virtual condition for a pin is the MMC plus the geometric imperfection, the geometric tolerance, let's call it, right? So the biggest I can get plus the quickest I can get. And the virtual condition for a hole, it is the MMC on the hole minus the geometric imperfection, right? I can grab that hole now. Grab the hole, and I can look exactly just at the worst case condition, which is my virtual condition, and I can also look at the virtual condition of the pin and just focus on the virtual condition of the pin. And now if I have a gauge, I can create another piece of metal. Let's call it another piece of metal that is going to be exactly this hole, something like this. We'll have my pin, which has exactly the worst case condition. I'm going to have any pin once I manufacture it, go to the worst case condition, which is the hole at the worst case condition, which again is also the size of the virtual condition for the virtual condition for the pin. So the diameter of the virtual condition, I can grab that pin once it's manufactured, put inside of the hole, and if it gets to fit, it will be already accounted for the maximum material condition and the geometric imperfection. And I can do similarly for the pin. I can grab a pin that is at the virtual condition of the hole, right? And grab that pin and try to put it inside the hole. Anytime you have a hole, the different sizes, I go my virtual condition. I create a pin, which is what I call a gauge, put it inside of it, and if it fits, it's good. All right. That was pretty much the review. Let's start with the new lecture, which is position. Okay, let me start right from the top. Okay, so it has been noted that the form and orientation tolerances allow the designer to apply a relatively loose size because I am controlled and also tightening up in what is your function, right? And the reason is because we're controlling the function alone. So apply relatively loose size tolerances while maintaining precision on those aspects of the design that are important to the part function. This is not the case for the position tolerances. GD&T position tolerances are an alternative means to change or baseline dimensions for locating features. After describing how to specify these tolerances, this will discuss the advantages of using GD&T. Okay, in other words, let's suppose, as I told you guys before, you guys have a part, right? This is my assembly. You guys have a couple of pins. In this case, you have 2 pins, and you have 2 holes. I want to make sure that I can go and I can assemble these things together all the time, right? Before, I only accounted for the size, plus and minus, plus and minus. Now, the problem is when I have things that need to mate with each other and they have geometric imperfection. It's a little bit crooked. It's not perfectly in line. Maybe it holds the size, but I know the crookedness on this pin, either external or internal. Okay, so we gotta do something about it. So let's say that I have a part, and the part looks like this. I'm just gonna make one hole. Okay, let's say that my part looks like this, and then my hole looks like this. And if I were to look at side view, my side view looks like this, and my hole looks like that. Right? Okay, so how do I define an axis of a hole? Well, it's kind of hard, right? Because I cannot grab a whole axis. You see, this has a hole. Can I grab it? Can I grab the axis? No. So another way for me to be able to grab a whole axis, I actually need to go inside and open up. As soon as I open up, like kind of like a drill that it squishes for an external feature, right? Kind of like when you have a chalk for your drill gun that it squishes and defines the axis and then it rotates. Well, the same concept will happen with a hole. It needs to go in and open up. Once it opens up, it defines an axis. Let's say that this is my axis, right? And my axis in this case, if I want to look at it on the side view, it will look like this, right? Now, where do I dimension from? My part is kind of crooked all over the place, right? So I need to fix a reference frame so I can actually start measuring from it. Let me also do the top view here, okay? Top view here, something like that, all right? And again, I'm going to make this guy also like that. And then my axis is all crooked all over the place. Okay? Now, what's the problem with this? I gotta actually find a way for me to find this axis and measure a reference to something. So if I were to measure, and I measure from here, or I measure from here, or I measure from here, it's not gonna have a reference stable place for me to define the axis. So I need to establish a datum reference frame. I am going to start by taking care of the bottom of my part, and I'm going to try to make it flat. Okay? So you know what? I want to make a more stable reference frame. I'm going to go from here, and I'm going to define a datum. And I'm going to call this guy, I don't know, let's make it flat, 20,000, and let's call it datum A. Okay? Now, at this point of time, I have created the bottom of the part, where my thing is going to assemble, and I'm going to assume that my assembly condition is going to be something like this. Let's see if I can do something really quick. Let's say that my assembly condition is going to look something like that, right? I'm going to grab this part and I'm going to stick it inside of it. Let's see, it's going to go here. I'm going to grab this part, I'm going to stick it inside of it, okay? So it's going to sit here in this part. And since it's going to sit in here, might as well use this. I will use my datum for my assembly here, and I will also use it for my part that is going to go inside, right? So I have started controlling now. Remember, when we're talking about datum, we are talking about theoretically perfect. Okay, theoretically perfect. Okay. This true bullseye, the bullseye here, I am going to be controlling is location of the bullseye, not by the size. So, for example, now that I have established the reference frame, I can go straight to theoretically perfect. And I'm going to put a box, and I'm going to explain you just a second what is this box about. Okay, I'm going to put a box in my location, my true position. I also got to take care of the left side as well as the back side. So most likely I will want to make maybe uh, perpendicular, right? So this can have a more better stable condition. I'm going to make this guy, I don't know, perpendicular to datum A, 52. It's a little bit better. And now start, instead of measuring for my imperfect condition, I can start measuring from the perfect condition, right? From the perfect condition. Okay. I may also want to take care of the back, right? So I'm going to do a little bit more polishing on this. And I will say, you know what? I want to make this guy perpendicular within 2 with respect to datum A and B, right? And let's call this guy datum B, and let's call this guy datum C. Okay. So if I were to draw this, datum B would be the left side, and the back of the card would be datum C. Now at this point of time, I have my axis, or kind of like my reference frame, where it will be just like in terms of the assembly condition. Datum A, datum B, datum C, right? Now what I have done, let me see, come over here and start. What I have done is I have located the true position where this bullseye is. Okay. Now, have I located the little plus and minus? I don't know if you guys remember that before you guys have like plus and minus. This hole was located maybe 1 inch plus and minus one direction, right? And maybe 1 inch plus and minus one direction. But this one is not located in plus and minus. This one's located in the theoretically perfect. We call this guy, the ones on the boxes, we call it basic dimensions. And they are theoretic perfect dimensions. Okay, so they don't control the position alone. I mean, they control the true position where actually the bullseye is. Now, let's say that my hole came and it looks just like this, right? How would I control it? Well, I need to control it somehow, and the way I control it is by having a tolerance zone, which is going to look like a cylinder. So we can make a different color. I'm going to make it green on the side. Cylinder. So cylinder right there. Okay, and it's also will be a cylinder here, right? And again, remember, this back is the same one as the one on the side view, right? It's the same back and back. So that cylinder is, I gotta orient this cylinder, the one that is here, right? Which is where my axis is going to live. And how am I going to orient it? Well, I'm going to be calling at the hole, okay, and I'm going to give it the size 1.00 plus minus 0.01. Right, that's this controlling the size. And again, it doesn't matter what the size is. The way that you establish the size is by extending or squishing, right? Either I squish for an axis to define an axis, or I extend inside the hole to define this axis. So I'm going to put a fish control frame to define the position of the axis based on this, on the position symbol will be something like this. Then I will have the diameter because I have a cylinder, which I'm going to call it 0.01, right? And then I'm going to say that I want to locate the cylinder, and I most likely want to locate it perpendicular to a surface. So when I go and I put the hole, I want to make sure that the hole is going to be perpendicular, right? So if I go, I don't know if you guys ever try to make a hole somewhere, you grab your drill bit, and you want to make sure that it's perpendicular to the surface that you're putting the hole, right? So I want to control it. I want to control it in this case. I'm going to control it perpendicular, right? So it's like that. It will be perpendicular to my datum C. And then I want to locate it. So you guys can see this is the bullseye. Now I control the location based on these two datums A and B. So A and B. So in other words, the first two locate and the first one orients. Okay. So while the plus and minus controls the size and form, this guy, the GD&T symbol, controls the location. Okay. All right. I'm gonna hope. This is kind of like the introduction. Let's say. Let's see if we can get a little bit more PowerPoint based. That would be it. Okay. There's a different way of thinking on how you locate things. This is what you guys have seen. There is a well-established language that allows you to communicate your design intent to the feature control frame. And for example, like the one that is here, let me see if I can draw it. That will make slightly more sense. Let's see, I'm going to put I'll do my best, I'll carry up. Like that. We'll try to draw it. So it seems to me that it looks like this. So something like this. Something like that. Right? And then it seems to me that it has two holes here. And they're blind holes. And then it seems to me it has one hole here, another hole there, and another hole somewhere here. And then go to the whole part, right? And then it goes into the top view and it's telling you, hey, you have these two holes. But before I start looking at my bullseyes, they establish a reference frame. And you guys could see here in the sketch that they call this right side, they call it Datum D, right? They call the back side, it was like purplish, I have purple. I have a bluish, I can use the bluish. So this guy, the back of the part, they call it Datum A. And it seems the bottom of the part, they went and they call it Datum C. And again, all of this is in the views that you guys see right there. And they say, you know what? Now I want to locate these bullseyes. My bullseyes are right there. So I want to first position the bullseye, and then I will give it the tolerance zone. So the bullseye is going to be based on Datum A, Datum B, and Datum C. So you guys will see in the top view, you guys have something that looks like this. And then it has a box, right? The box is telling you know what, go theoretically perfect to the back of the part and locate 0.450 away from it. If I am locating from the back, I also need to locate from the right side view. And that's what you guys will see there, that there are two dimensions, one right there, and they put another boxes. And again, boxes indicates theoretical perfection. So that means I could do a chain dimension, or I could do a baseline dimension, and it really won't matter because they are theoretically perfect. I just try to say, you know what, theoretically perfect, back to where the theoretically perfect plane is, define the true position. Okay, now what else do I have? So I got another location. Now I can control the bullseye. I control the bullseye by defining a cylinder that is going to go to the part, and that's where my axis gets to live. So how do I call that? Well, so they have a view where they can see this. They give it, there are two of them. You can have like a little center line somewhere in there, and also use center marks. And they say the size, what they want to, and then say, you know what, I am going to control the position of that cylinder, so my axis gets to live within it. It's going to have in diameter, because it's a cylinder, the size of the cylinder diameter is going to be 0.005. The M, I will talk to you guys about it a little bit more. But let me also say, it's telling you when this hole is an MMC, you will get 0.005 of tolerance. Then I'm going to start to locate and I'm going to start to orient. So the first one, they say, you know what, I'm going to use Datum D. It actually seems to me that they define one more datum. So in this case, the top of the part here, they define it as Datum D. You can see it on the view, on the front view that you guys see there, right next to me, right? So this Datum D, you say, you know what, I want to make it perpendicular. So I want to make that hole, and it's going to be on this surface. It's going to be perpendicular. So I'm going to call this by D. And then I'm going to locate it. Because in this case, I'm going to locate it with respect to Datum A first. Then A is the back of the part. That's where this red comes about. And then I'm also going to locate it with respect to Datum B, and B is the left of the part, right? So if you guys come over here, you guys will say A and B. A, these are the holes that I'm doing. And again, it's this one axis. This is the axis, this is the axis. These are the two holes. I'm controlling the position with respect to Datum A and Datum B, as you see right there, and I'm orienting it with Datum D, and Datum D seems to me is this surface, the one that is red. There are three requirements for using positional tolerances in a drawing. Datums must be identified. Basic dimensions must be used to locate the features. And again, datums must be identified because GD&T is a well-established language which allows you not to measure in perfect conditions, like the ones that were here before, I gotta go back to perfect conditions. Right? And the basic dimensions will pretty much will allow you to locate the true position, and then the GD&T, the feature control frame, will tell you the size of your cylinder, your part needs to live somewhere within it. There must be at least one feature to control frame specifying the position tolerances. Well, if I want to have positioning with respect to something, either I'm going to orient it with respect to something, or I want to position it with respect to something. Again, this is kind of like the same thing that I was telling you guys. This is the cylinder. My part gets to live within the cylinder. My axis, or once the part comes, needs to live within this perfection cylinder. The basic dimensions pretty much identify the perfect condition of what this bullseye is. So if I were to do chain dimension, or I want to do baseline dimension, it really doesn't matter, because I am focusing on the assembly. How my things are going to go, right? Okay, so again, this is what I was telling you. Here's the this is the part that is here. These are the datums, right? I have my axes, and the true position is the bullseye, right? And this diameter, the cylinder, is the tolerance zone that leaves perfectly positioned and oriented, in this case, to that true position. Then my part comes and it gets to swivel around. So let's actually make that make sense of that. So I have a part, and I'm going to have my back of the part, right? And then this is my tolerance zone. This is the true position. This is, let's call this guy datum A, which is again is the same one if I want to look at it on the side. Let's call this guy datum B, and let's call this guy datum C, right? See. And again, if you guys want to look at it in 3D, this guy will look something datum A, datum B, datum C. Now I got my part, I put it on top of this, and my part will look something like that, right? So this is my part, okay? And then I put it against this guy, and my part will look something like this, right? And let's say my bullseye, remember that my bullseye is perfectly located based on perfect conditions. So let's say my bullseye, it is going to be somewhere there, and the tolerance zone of the cylinder will be somewhere there, okay? If I have this bullseye and I want to position it, I gotta give it basic dimensions, right? Another basic dimension there. Basic dimension, right? True position. The size of the cylinder is going to be given by my feature control frame. I'm going to come over here, feature control frame. Again, I will have a size 1.00 plus minus 0.1, and use any of those ones. We will talk about actually what will you use, and then you have a position, and then you have a diameter. The diameter is this time, right? What's the diameter? Now my part comes, and let's say that my part comes and it looks like this, right? And it seems to me that in this case, my axis of that, maybe it would be here, somewhere there. And I don't know if you guys could see, my part axis, which is this one, lives within the tolerance zone, which is the cylinder. This cylinder right there. And again, this is the blue one, and then the intersection of those two blue lines are meant to be the location of my axis. It lives there, right? So even if my hole were to move to the side, or up or down, still within the, so I'm controlling where the axis lives within my tolerance zone, which is perfectly positioned. Right? Now let's say that I were to look on the side view. Let's see how it looks. Well, my side view maybe looks like that. That's where my hole is, maybe. And if I were to look at the axis, maybe my axis lives there, right? This is my hole. You have to catch it. You have to see the hole slightly better. So this is a hole, right? My axis gets to be within this tolerance zone, which is perfectly oriented to datum C, perfectly located to datum A and B. So I gotta let them know that I want that condition. Then how do I let them know? Well, I let them know with datums, but oriented to C, located with respect to datum A and B. Boom, done. Then my part. Now, every time that they inspect it, they will go say, okay, I gotta first find out the perfect condition, right? Establish my theoretically perfect graph, any part, put it there to those datums, and then whatever my axis is needs to live within the cylinder, which again is given by the feature control frame. And again, this is what you guys see here. All right, so what do I have here? This is kind of the same concept I'm telling you, but with less sketches. Hopefully it makes a little bit of sense. Once the true location of the features are located, the tolerance zones are cylinders with diameters equal to the specified tolerance, centered on the true position, the bullseye, extended through the thickness of the feature. And again, this cylinder will always be perfect, theoretically perfect. In this case, I have datum A, and the datum A is this bottom, the cylinder, which is 0.24, perfectly 90 degrees with each other. Okay? Now my part gets to live with it. It could be out of position. You can move this hole to the left and to the right. You can tilt the axis in and out. Okay, so for example, here I move it. This is right on the money. This guy, I'm gonna say, you know what? I'm gonna move my hole maybe a little bit to the left. So this is the axis of the hole that I came. The orange is the true position, with the tolerance zone is the orange. The blue is the true position, and the orange is the tolerance zone. The hole that you guys see there, it is the hole how it was manufactured. So in this case, this hole was a little bit to the right, but still within the tolerance zone. In this case, the hole is a little bit tilted, but the axis, even when it's tilted, the axis of the hole still lives within the tolerance zone. Okay. Now, let's compare what happens when. Why am I making you do this? Why am I teaching you this? Well, let's talk about it. Let's talk about the advantage of having a plus and minus. What is the disadvantage of a plus and minus? Controlling only the size, plus and minus for locating things, for positioning things. So let's talk about the advantage. Let's consider that I have two main parts, and in these main parts, I did not include any, let's say, any GD&T, right? We just have it like the way you guys see. So I have two main parts. One where I have a plate with a bunch of holes, and I have one where I have a couple of pins that are going to sit on top of each other. So I'm going to grab this plate, this part, and I'm going to stick it in those holes. Okay. So in there, you guys will see that I have a distance 2 plus 7 minus 7 thousandths. 2 plus 7 minus 7 thousandths to controlling the size, I mean the location. And then I also have the size controlled by this diameter. Okay. Now, if I were to look at this hole, that would mean, I kind of do this in the morning, for once I put a plus and minus, let me try to put this right next to it, maybe A. Once I put a plus and minus, it indicates that, and again, you guys could see this, let's imagine that this is the 2 inches, right? So that means that that distance can grow a little bit, or maybe less a little bit, right? You have an upper limit and a lower limit. And again, you can also do the same thing right here, your plus and minus, maybe a little bit bigger, maybe a little bit smaller, right? So if I were to look at the tolerance zone, it will look actually like a square. That means my hole, the black one, I don't know if you guys could see the black one, hopefully the perfect condition, right? The black one. What is the black one? This is the black. The black one, which is the perfect condition, can shift to the right. It can also shift to the left. And it can shift by this little plus. So, for example, the green one, right? So the green one axis, I'm going to assume it's somewhere there, right? Because it shifted to the right. And the blue axis, the blue hole that's here, I'm going to see somewhere there, right? So they can shift to the left, and they can shift to the right based on my tolerance zone. And I can also shift upwards and shift downwards. And if I were to look at the tolerance zone, it will look something like this. Okay. So now that we understand this, let's say, you know what? I am going to start moving things in terms of making see if it's going to fit, right? So what I can do is I can look at these meeting parts. In this case, I have the pins, and on the bottom, I have the holes. What I can do is I can grab these holes, because I know I can move to the left and to the right, right? To the left and to the right. And either the pins or the hole, I can move to the left and the right. Well, let's do one thing. I can grab those pins. And I can shift them, right? Remember, I have 2 holes right here. Let's call this guy the holes. Let's call this guy the pins. So I can grab those holes. And remember, you have 2 green lines that represent your how much out of position can move. So I'm going to grab them. And again, the perfect condition will be this black one. Let's call this black, this one, right? But instead of putting them in the center, let's get them out of whack. I'm gonna move it to the side. I'm gonna push him so that my axis actually lives on this blue one. Right? So shift them. Yes. So now my hole move to this guy move this way, and that one move that way, and now my axis for the whole ones that actually got manufactured is this one and this one. Okay. Both of my holes have a 0.375. Actually, this guy is 0.375, right? So I can do the worst case condition for the hole and the worst case condition for the pin, for the MMCs. In this case, you can do, since I move it to the right, now this distance between the axis that I move it to the left and the right is not the biggest, which in this case will be 2.007. So again, I shifted my holes to the right and to the left, right, to move it apart. I also made it the worst case condition for the hole, which in this case, the worst case condition for the hole would be 0.361, actually 0.375. That would be the worst condition. Would be the smallest, right? And I can also do the same concept for the pin. Since I got in my both of my holes moving to this way, maybe I can do the same concept with my pins. But now, instead of moving into the outside, I want to move into the inside. Now they will be right here, touching my tolerance zone, which is the green one. Okay. Now, what am I telling you this? Well, I could grab my holes and push them towards each other. Okay, and I can grab my pins and push them against each other. Right. But if you want to do the math, and I actually don't want to do the math because I'm running out of time, you guys will notice that in this case, when I have a hole and I have a pin, they both align with each other. See, this pin will go into the hole, even at the worst case condition. Now, the problem with this is that this is a square tolerance zone. In the regular plus and minus world, what would happen if I were to look at different conditions? Maybe I went to the left and I went to the right, but in reality, you might also have out of position that is diagonal, maybe somewhere in the middle, right? So you guys could see here, it works. It works when it goes to the right. It works when it goes to the left. But when it goes to diagonal, it might not work. In fact, it won't work because it's larger when you go to the side. So, and it won't work because my tolerance zone, I'm gonna show you, right? So, if I were to have an axis that I move it to the left, it works. If I move it to the right, it works. If I move it up, it works. If I move it down, it works. If I move it all the way over here, right? Now I have places where this guy is actually a little bit larger, right? So, in fact, let's say that I have to go in terms of the diagonal, let's see it. So this guy is actually larger. And in reality, what I'm looking for is to do a bullseye. And you see this distance is actually larger than this distance. So I am reducing the amount of, so I'm controlling more the function, I guess, than if I were to do it just a square. This is what it's trying to tell you, right? So this is the square tolerance zone 7 by 7. I will have to reduce my tolerance zone to actually mimic. It's actually better just to do a circle. And this is the bullseye, you guys can see it. Let me see what I say. However, if I tighten tolerances, I make things more expensive, and I might throw away parts. If I still want to keep on using size tolerances, I will need to tighten my tolerances to 0.05. Well, I don't want to do that. And I also got some parts that I might be rejected if I were to lower my tolerance zone. So I might want to just do a tolerance zone, which is going to be cylindrical. So this is the way you will call out a position. You will have to put your basic dimensions. You will have to always establish a datum because you have to have a datum to have a position. You will be controlling your form with this plus and minus. You will controlling your position with this plus and minus. When you have an M, it indicates an if then else statement. If your part comes at MMC, I will give you 7,000. Okay. Let's come over here. The next one. It is coming your way, so let me see. I'm not sure what is this one about. Come on, computer. Another advantage of using tolerances is the datums are so much better, so that the ambiguity is reduced and the clarity is increased. Right? If you guys have plus and minus in terms of locating holes, your part could look something like this. And again, where do you measure from? Where do you measure from hole to hole? Where do you measure from the surface to surface? When you go and you are measuring from theoretically perfect, okay, then I am able to measure different parts that are being inspected in an equally manner. So I can go over here, right? And I know my part might look like this, right? But once I place the part in theoretically perfect, then I can, let's see, let me place it now. Now, based on this, I can go and measure from theoretically perfect every single time. If I have a part that looks like this, or maybe I have a different part that looks like this, every time I can go back to theoretically perfect and find that tolerance zone, and then my hole needs to be within it. Right? My hole needs to be within it. Position and oriented with respect to it. Okay, now that you guys have a brief understanding of what GD&T is, I'm going to have a little hickey that I drew today in the morning. This is the tolerance zone of GD&T. Let's say this is my hole that it has to be at perfect size. Let's say at the design size. Let's first find the bullseye. Then, if my hole, I'm going to make this guy black. This is the same one that you guys just saw in a second. If my hole moves to the left, my axis might be here. If it moves up, my axis might be here. Move down, the axis will look here. To the left and the right, the axis will look here. And if it doesn't move as much, well, I will still live within this red tolerance zone, right? This red tolerance zone. Now, that is the reason. This is the tolerance zone for position. Not any plus and minus anymore. This is what it's telling you that your axis needs to be. So that's why in your feature control frame, you will have a position, you will have a diameter, because the diameter is this guy, right? And then you orient and locate that datum based on your datums, right? Usually the first one will control the position. So you will want to look for a surface that is perpendicular to where the hole is. I mean, the location, to make it perpendicular to where the hole is. And then usually the second two will control the position, right? For example, this guy will be, I don't know, datum A, and this guy might be datum B. So then this A and B will be here, right? Or you're controlling the position. And this guy might be the back of the part, and you will control it based on that guy. So let's call it as datum C, the back of the part, and you will just call it out. Now, in terms of putting things together, there are two different type of conditions, the fixed and the floating fastener conditions. What do I mean with fixed and floating? It is if I were to have two parts, let's see, two parts, and I want to put them together, there are two conditions. Once where I have a clearance hole, and then the second one, let's say, it's threaded, put the axis there, and then the other one where I have a clearance hole, actually just clearance the whole thing, and then I grab my pin, and in this case, my pin will be, this is my bolt, I get to sit on it, right? So we'll go clear on the first part, this is part one, and this is part two, right? So we'll go clearance on the first one, clearance, and then on the second one will be a thread. Okay. So we call this guy fixed fastener condition. And then this other one, in order for it to bolt, I'll have thread here. And here I'm going to have another nut. This guy is going to go all the way through. Right. So the bolt will go through both of the parts. I have physics. Okay, 42. Thank you, man. You got this guy, you put it all the way through, and this guy is going to be floated because my bolt floats with these two parts. If you guys want to calculate the tolerance, your tolerance that what actually goes in your feature control frame, again, we don't have time to actually talk about how this came about, but the tolerance that comes over here in your feature control frame, again, you got data. Let's call this like data B and C. Let's call this like data A, B, and C. And here you will have an M, and the tolerance that goes here is different for fixed and for floating. So the tolerance that you would put for the floating right here. Floating is going to be H minus F, and for fixed will be H minus F. So H will be the whole maximum material condition, and F will be the fixed maximum material condition. Now, in terms of actually using these formulas, we will believe that the only way to learn this is actually doing it. I think if I just go all the time trying to do talking about this lingo, it's most likely will confuse. I'm probably already like super confused. So don't worry about it. I think the best way is to practice. And the more you do it, and I want to do my best to do a lot of them most likely during the lab, because I have more time. The more you do, the better you get at it. We just do. And after we do like 20 of them, you guys are going to start getting the hang of it. All right. Let's stop the share. Let's stop my recording. Good afternoon, engineering 2. Let's talk about position. What the frick is position? All right, so hopefully I'm going to make sense of this. I'm going to do my best. Okay, so here you guys will notice that I have a pin, I have a pin, and I have a hole. Are we all good? Right? If I were to have a hole, and I'm just going to do a hole by itself. This is my wiggly part. And it has a hole that is maybe crooked. And I were to have a wiggly pin. And if I only were to be a single hole, and this is my hole, this is my axis, this will be my pin, your fit chart will work just fine. Because the fit charts, they take care of your tolerance, which pretty much it is your dimensional tolerance, which automatically they control the form, right? It has to live within the biggest I can get and the smallest I can get. And so in your form will live within it. Does that make sense? I also have my GD&T form variations. This is here will be my D for dimensional tolerances, and my form variations will live within it. Does that make sense? I'm trying to say, you know what? I want to give you as much upper to lower limits. This is the lower limit, and this guy is my upper limit. I want my part to be within the upper and the lower limit, and if I want to refine the form, I get to do it within the tolerance that is within it. At this point of time, I have a tolerance zone that lives within the other tolerance, the dimensional tolerance. This one here is the G, geometric tolerance. But I'm only controlling the form. I'm not, let's call this guy flatness. I don't know. And assume this guy is actually like a rectangle. Okay? You guys will notice my dimensional tolerance, which is my upper and my lower limit. My lower limit and my upper limit, it is these two boundaries on the top. And the form can be refined with a geometric symbol which control the form. Which in the case that you guys have done flatness, right? We have talked about it in the lecture. Now, dimensional tolerance can control the form, especially if you don't have nothing to align it with. Like if I were to look at this hole by itself, and even if I were to be crooked, all I gotta need to ensure that this guy is gonna meet with it. Does that make sense? Now the problem starts happening when there is more than one hole. Now we got two holes. Because if one of them matches and the other one don't, then we got big trouble, right? We got big trouble. So, how do we take care of this? Well, we do it with position. And let me explain you how it works. I am going to come and I'm going to make a wiggly part. Okay, wiggly part, something about yay. Wiggly part, wiggly part, wiggly part. I'm going to put two wiggly holes. And I'm going to grab a part like the one that I just showed you. And I'm going to put two wiggly pins. Wiggly pin, wiggly pin. Okay? Let's start focusing on one of them. Well, first of all, if I were to look at this one, my front view will look something like this. And if I were to look at the side view, it will look at something like this. Yes? And I can also do something similar in the top view, it will look something like that. I have one hole that looks something like this, something like that, and maybe my holes are crooked. Maybe are somewhere like that, somewhere like that, and then this guy might be a little bit crooked that way, and maybe I click something like that. You see my holes all crooked? Okay, I want to ensure that the holes are related to each other and they are related to my datum. Right? So I am going to first most likely establish my reference frame. Let's do our typical. I'm going to say, you know what? I'm going to try to control the surface, the bottom. I can also try to control the left side, make it a little bit less crooked. Let's define datum A as the bottom. Let's define the left side as datum B. Let's refine it by adding flatness at the bottom. And let's refine datum B by making it perpendicular to datum A. That's why the A and B becomes perpendicular to each other. Let's also refine the back. Let's refine the back. And let's call that guy datum C and make that guy perpendicular to A and to B. Does that make sense? Now I have a reference frame that I can actually start working with. Also, I need to consider that even when I have taken care of the surface, my surface is not perfect. My surface might still be wiggly. That makes sense? So I am going to measure when it actually gets to be produced or it gets to be inspected. I'm not going to be measuring from my imperfect part. I'm going to be dimensioning from either a granite table or a milling table, or maybe we'll have a lathe that will hold the part and will rotate, right? Much better than my part. And all my dimensions will originate from the datum to where the axis is going to be, right? And in order for me to define the axis, I need to go inside of the hole and expand. The same way that I told you for the pin, it's just like a drill, right? You gotta expand and define the axis. Okay, how do I control the hole? Well, I am going to expand and define the location of that one. I'm gonna expand and define the location of that one. And that means it will define an axis that looks something like this. And it will also define an axis that is actually crooked a little bit. How do I control it? Well, it's just like a dart. When I go and I throw my dart, my dart needs to be within my bullseye. And if it's within my bullseye, it will be in spec. Okay? So I need to make a bullseye. And my bullseye needs to be perfect. Yes? So let's say that my bullseye is actually here. And I'm going to put a center line. And it's going to be there. That's where my drawing is supposed to. That's where my drawing calls it out. Let's say that my perfect hole is here, like in my model. Right? So my model is perfect. 0.0000 till infinity. The real one is the one below. You guys see it? Well, if I go and I need to ensure where my bullseye is at, which is the perfect condition, I need to dimension it from my datum. So I'm going to go over here, and I'm going to dimension it from my datum. Okay. I'm calling out to the perfect position. So my perfect position cannot have a plus and minus. And the way I tell it that I don't want to have plus and minus, I put a little rectangle. Professor Escalona, how do you do the rectangle in Inventor? You double click on it in the same way that you do reference dimension. There should be one that says basic, and it will make a rectangle. Okay. And since this is perfect, I can literally go and forget about stack ups. You guys did stack ups not too long ago, right? Dimension and stack ups, plus and minus, and finding your upper and your lower limit, right? So I don't have to worry about it because this is perfect and that one's perfect. Okay. That one will allow me to know exactly where my bullseye is. Let's also go from the bottom data and give it another perfect location. On top. Now I know exactly where my bullseye is at. Now I need to give it a diameter so that when they throw the dart, it needs to fall within it. Yes? So let's put a diameter, make it with purple. My diameter, let's say that my diameter on my bullseye is here and is here. Well, that diameter, I need to call it on the drawing. So I will go with the drawing wherever I get to see the hole. And I will say diameter 2 times whatever that it is, plus and minus, right? And then I will put my feature control frame. I will call the bullseye, which is the position symbol, right? I am creating a bullseye which has a diameter, so I'm going to go give it the diameter, and then I'm going to give it the size of that bullseye. Cylinder, actually a cylinder. And then at this point of time, my bullseye, which is a cylinder, lives in 3D space. So I need to tell it where it's located and where is it oriented to. Okay? Let's say that I want to orient it perpendicular to the back. Right now, this is holes that I go all the way through, right? And I want it to orient perpendicular to the back. This is the holes. I wanted to make perpendicular to this. When you go and you make a hole, you most likely want your drill to go perpendicular, otherwise your hole is going to go sideways. Yes? So, you say, I want it perpendicular to datum back, which is datum C. Boom. Are we good? And then we say, you know what? I made it perpendicular. Now it's perpendicular here, but I still want to locate it with respect to the bottom and with respect to the left. Well, I know what are those. I define the datum A and I define the datum B. Yes? So I'm going to say, I want it located with respect to A, located with respect to B. Are we good? Right. Right now, I'm just grabbing the bullseye and I am defining it. The way I define it is by defining the bottom, defining the left, and defining the back. I start that way. Right. As before I actually define the bottom, the left, and the back, I had to have qualifiers that orient each datum to each other. So I have flatness, that's why I got perpendicularity. I have a reference frame now that I can refer to, and then I go and I start locating my bullseye. To locate my bullseye, I need to have perfect conditions, because if I don't do perfect conditions, that means I am locating with respect to this, or maybe that one, or maybe the middle one. I don't want plus and minus here. I want perfect condition to the datum. And to be able to do that, I have to do this. I'll give it a basic dimension. That makes sense? Okay. Now, what's going to happen? My cylinder was oriented perpendicular to the back, which means if I were to project it here, it will be there, and it will be there, and it's a cylinder. That's the cylinder. You see it? Yes or no? And if I were to look at it from the top, my cylinder is here, and my cylinder is there, my cylinder is here, my cylinder is there. And then let's make it a little bit bigger. That one, and that one. Now, my axis on my crickety part needs to live within it, because if it doesn't live within it, I'm out of spec. Yes? So I'm going to come over here, and that axis is this one. So it seems to me, based on my side view, it fits inside of it, right? It's not too crooked. But if I were to look at the top view, my axis got out. Now, how do I guarantee? Right now, I'm just explaining you, right? First, I have a tolerance for my bullseye needs to fit within it. How do I guarantee that I can come up with the size of this bullseye and still allow it to fit and allow it to get other parts and do the same thing? Well, I gotta make a bullseye for this, and I gotta make a bullseye for this. Let's imagine what really happened. I'm going to make a hole, and I'm going to make two circles. Let's say, I'm also going to do the same. Let's actually start with the pin. I'm going to start with the pin. And again, my pin can go plus and minus, yes? So let's say this one, it is the smallest I can get, and the biggest I can get, I'm going to make another one, which is about here. Are we good? Okay, for my pin, which is the worst mating condition? When it's small or when it's big? Which one's the worst mating condition? When it's big, yes. So might as well disregard the small one. Let's just look at the worst case condition. Because again, the whole idea is to ensure that they will always fit. Yes? So I'm going to grab my hole and I'm going to be using the MMC. Now I just told you that my axis can shift sideways, up and down, left and right. Yes? So I am going to want to assume that this is my bullseye. This is where the perfect condition. This is where my part be at the MMC, which is the biggest I can get. At this point of time, when it's the biggest, it cannot have any form variation, because if it becomes a little bit of crookedness, it is going to get off my upper limit. And if it gets off my upper limit, then I fail. I lose the D. Remember, GD&T, so the D is gone. No bueno. So at the perfect condition, let's say that is right now, but I got to give it some wiggle room, right? So let's say that my wiggle room, I grab my part and I shift it to the top. If I shift it to the top, this guy will look like this. So this circle, shifted to the top, will look like this. You guys see it? Okay. I'm going to move it to the right. So I'm going to shift it to the right a little bit. And it looks like that. And again, I'm only looking at the biggest pin. And I'm shifting it up, down, left, and right. I'm going to grab a pin, the biggest pin, and I'm going to shift it down. It will look like that. I'm going to shift it to the left side. And it's going to look like this. And I also can lift it sideways, downwards, upwards, sideways. Just start moving it all over the place. And if you were to notice, I'm actually creating a boundary. I'm creating a boundary of all the sheets, left and right, left and right. If I were to grab that boundary and put it on the right side, and I were to put one of those holes and put it on one of the edges, again, we're doing MMC, right? The biggest I can get. So put it right there. And I were to measure the distance of this one. This guy is my G, which is the diameter. Now, let's write it again. I'm going to put my bullseye. I'm going to redraw it again. Put it here, put it there. I'm going to put my perfect MMC right here. And I'm going to put the boundary outside. And I'm going to grab half of this, half of that, and I'm going to put it here. This one right here, that is my geometric tolerance zone. I can grab my MMC, which is the biggest I can get, and I can shift it to the right, shift it to the left, shift it up, shift it down. And it doesn't matter where I put my pin, as long as I relate it to my datums. That's what I got to put it with basic dimensions. Let's call that the true position. True position is where the bullseye is, and it has a certain diameter that I call it out in the feature control frame. My hole has the D, which controls the form. In a worst case condition, it will be at MMC, the biggest I can get. And I'm giving it this amount of G, geometric tolerance, so it's able to move to the left, to the right, up and down. And it shouldn't, the axis shouldn't get out. If I move it to the left, let's say on this corner, that means my hole will be somewhere there. But it still will be within my boundary. This boundary, we call it the virtual condition. The combined effect of size and geometric imperfection that allows for things to mate all the time. Does that make sense? So now what would happen? This is the pin, right? This is the pin. Well, I'm gonna do something similar with the hole. So I'm gonna grab the pin, which is my geometric imperfection, the worst case I can get, and I'm gonna create another boundary. Which is gonna be my hole. I am going to put hole that's gonna look like this. And again, this is the boundary of the hole. Question: what is the worst mating condition of what is the worst mating condition of a hole? When it's the biggest or when it's the smallest? When it's the smallest, because my hole is small, it will be hard to fit in the pin. Does that make sense? Let me make a hole on the side view, and let's make it at MMC, which is like this. And now this is perfectly straight, right? Now let's make it cricket. What happened to a pin? So if I were to have the pin, and my hole were to be perfectly straight, even at the worst case condition of the hole, which is called the MMC, will have to fit in the MMC of the pin. So again, both of them will be in the worst case condition. The big one and the small one. And it will fit. But that happens when it's perfect. And nothing's perfect, by the way. Right? So what happened to the hole? If I were to leave this guy the same way it was and make my hole a little bit cricket, it actually becomes smaller. Don't you guys see it? Can you grab that pin and put it in something that's cricket? Let's put something here like a plate. Can you put that pin in this hole and see the flush? No, why? So it became smaller, right? Can you grab that pin and put it inside there? No, I won't, right? So the way we make it work is say, you know what? Let's grab the pin. Let's account for the biggest I can get, where you are going to have a geometric imperfection, your dimensional imperfection, and let's give it a little more to account for the wiggleness of it, of the pin. Still talking about the pin. So let's say this guy is my G, this guy is my D. Yes? And then grab the hole. Grab the hole. Give it a little bit of wiggleness. Which is going to be my G for the hole. And then do the dimensional for the hole. So in other words, I have this guy twice. One for the pin, one for the hole. One for the pin, I run out of color. One for the pin, one for the hole. And even when my hole can also vary in shape and become smaller, even at the worst case condition, which is the virtual condition, the hole can have to still be bigger than my shaft, even when it's at the biggest condition and at the crookedest condition. Does that make sense? Virtual condition for a pin, it is the biggest I can get plus the crookedest I can get. And the holes in the hole got smaller. The worst case condition for the hole, it is the smallest I can get, and then take away the crookedness because it makes it smaller. Does that make sense? Those virtual conditions, then, to make it safe, I'm going to make it even bigger. Running out of papers. To make it even simple, I'm going to make it even bigger. So I'm going to grab the pin. I'm going to get dimensional tolerance, and then I give it a little bit more for geometric imperfection. I'm going to grab the shaft. I'm going to give it a little bit gap from here to there. Call it an allowance. And then this guy here will be the wiggle room for the hole to get out of imperfection. And then give it a tolerance here for the size. So this is the D, that stands for the size. This guy is for the G, which is for geometric imperfection. Imperfection. The same thing with this one. This is the G, and then this one is the D. And you guys will notice, even when my hole can be big, and it can have crookedness, and when my hole can be small, and can also have crookedness, at the MMC, when the hole is the smallest, or the shaft is the biggest, have crookedness, it will still fit. And if my shaft moves away from MMC, which is the biggest I can get, towards LMC, to the smallest I can get, it will give me extra. You guys see it? Or am I going too crazy? See, I have a better images. Let's see if I can show it to you. So, sometimes this topic is kind of hard to explain, which I should come up with better images. Let me see if I can show you one. So, let's take a look at the strains, because the strains is really similar in terms of the dimensional tolerances. Okay, so let's say that I have this condition. Okay, so that I have a hole. It's over there. It's half an inch. Lower limit, over limit. I have pin which has lower limit, upper limit. Right now, if the both will be at the worst case condition, which will be 0.5 and 0.5, and will barely fit, assuming that they're perfect. Yes? Yes, yeah? All right. Now, let's start making things a little bit crooked, which in this case would be the G. I got them the same size, and it's very crooked. Then another one, and then another crooked. Yes? All right. I know that if I make it crooked, they didn't fit. They won't fit. So let's make this boundary and find out what it is. This guy got the combined effect of size and geometric imperfection. We call it a virtual condition. The same concept over here. You got the combined effect of size and geometric imperfection. The smallest I can get minus the crookedness, because I made the hole smaller. And for this one, which is the pin, is an external feature, it is the biggest I can get plus the crookedest I can get, so that we can find a worst case scenario. Yes? Now, if we can go and we can look at the virtual condition and account for this imperfection, I can put the diagram here and there. So this is how much I allow for this one to move, and this one how much I allow for this one to move. Yes? The virtual condition for the shaft, it is the biggest I can get plus the crookedest I can get, which is what? What's the biggest I can get? 149. What is the crookedest I can get? Which is 495. Yes? How about this one? What's the condition of this? The smallest, yes? Which is an MMC. Which is a 0.5. Minus the crookedest I can get, right? So the hole becomes smaller. We're giving 495. Now, my shaft at the worst case condition, my hole at the worst case condition, and we still fit. This is the biggest plus the crookedest. This is the smallest plus minus the crookedest. Does that make sense? Okay. This guy has a name. And the reason why it has a name, it is because it allows you to use what we call functional gauges.
The way you check this is you may check it with a CMM. The CMM is like a probe that it touches in the part, and then it creates a 3D model, pretty much. And it allows you to find out if your part's on spec or not on spec. But that takes a lot of time, right? So might as well, we can combine the geometry and the dimensional imperfection into one single thing. For the pin, the biggest I can get plus the crookedest I can get, I can create a gauge, a piece of metal that is to that virtual condition. And make it. Grab my pin, whenever 100 of them, grab the first one and throw it inside of it. Did it meet? Well, if it fits, it is most likely because it's geometric imperfection plus its size imperfection are under my boundary. And I still gotta go back and double check local measurements, right? Because I still got my upper limit and my lower limit. And we're there. I can also go and I can do something similar with the pin. I can, with the hole. I can grab the hole and find its virtual condition. Which is the virtual condition of a hole? The smallest I can get, minus the geometric tolerance, and manufacture a pin that is to the worst case condition, grab a pin, stick it in there. And if it fits, you are guaranteed that at the worst case condition, it will work. And as my part gets away from MMC, my hole will get bigger, yes, which will allow for better position. We call that the hole.
How does apply to
for transitional fits and interference fits, you usually don't put position, right? When we have, by the way, we're not done this, you're going to watch the rest of the lecture. I just wanted to explain what it is. Usually when you're putting things together through a bolted condition or through a interference pins, you are joining things together, usually you have two types of situations. We call it the fixed fastener situation or the floating fastener situation. Fixed fastener is when you're screwing things, because once you screw, that thing will not move. And the floating fastener is when you have a plate on the top, plate on the bottom, you grab a bolt and you go all the way through, and then you put a knot at the end. That's the floating fastener. You guys are gonna watch the lectures for this week, and you're gonna learn about it. And also the formula. Does that make sense? Okay. I think that's where I wanna leave it. I don't wanna go too much into that, which I can already did, but it's okay. I'm gonna hope that you guys are, and if you didn't get it, don't worry about it. Just watch the video 20 million times until you grasp it, right? And if you still don't grasp it, we'll ask Ash, and maybe he can explain. Does that make sense? It's all good, right? And again, don't worry about it. We're barely introducing it to you, so it usually takes time for it to sync, right? You still got 3 weeks of syncing, right? Hopefully, after we do many quizzes, and we'll sync better. Does that make sense? All right. Don't forget to watch the videos. I'm gonna print the quiz right now. Yes. Okay, so I have the exam. I have them put them on the gradebook. If you wanna see them, I can show them to you. Okay. Let me just give you the quiz, and then you can come and ask. Okay.